So welcome to our final section of chapter 4, which is 4.4. They do list on the slide and in the book of 4.5, which is basically an online section about simulations, but we never plan to cover that. That's not part of the course. It won't be on any of the tests or assignments. So for us, 4.4 is the final section of chapter 4. And so this chapter about probability, the first three sections, which we introduced previously, talked about basic concepts of probability, some manipulative facts about calculating probabilities, the addition and multiplication rules, complements, conditional probabilities, things like that. And so today, our final section that we're going to cover is on counting techniques. 4.4 is about counting. So what does that mean as a key concept? This section requires much greater use of formulas as we consider 5 different methods for counting the number of possible outcomes in a variety of situations. Not all counting problems can be solved with these 5 methods, but they do provide a strong foundation for the most common real applications. So why do we focus on the idea of how to count things when dealing with probabilities? Well, let me reiterate that the classical approach as described in earlier sections for determining a probability of an event is that the probability of an event A can be thought of as a fraction. We know that probabilities should be a number between 0 and 1. But in particular, if you're thinking about the probability of a particular event A occurring, like the probability of flipping a coin 5 times and getting 3 heads or something like that, then the classical approach to determining that probability would be to count up the number of ways for the event to occur and divide that by the number of ways, and that's when these are equally likely, for anything to occur. And so the idea here is that there's counting involved. When you're counting up the ways that something can happen or that anything can happen, that's where the counting techniques come into play. So a simple example where we wouldn't need to use formulas, if I said, I'm going to draw a number from a bag that has the numbers from 1 to 100 in it. So there are 100 tiles with the numbers from 1 to 100 on them. And I'm going to pull a number. And I want to know the probability that I get a number that is 10 or less. Well, then that would be the event A from the procedure of pulling a number from the bag. And I could say that I know the numbers of the tiles, so I know there's 10 ways that I could get a number from 1 to 10, and that there's 100 ways that I can get any number, and so that's 10 out of 100 as my probability of getting a number in that range, which simplifies to 1/10. So that's, in that case, the idea of how to count up the possibilities are so trivial that we don't have to focus on how the counting was done. So what we're going to do when we look at these 5 different methods for counting things is we're going to look at ways of counting up things that are not so trivial, but have a certain pattern to them or a certain structure in what's going on that we can use formulas to help us count up something more complicated. So that's the idea. So having said that, try to think of an example. I just gave an example of pulling numbers from a bag and came up with a probability of 1 out of 10. So to put your mind in the framework of trying to think about what the probability of something happening would be and having to count up the ways it could happen and divide by all the ways anything could happen, try to think of a simple example like the one I provided. Could be anything. But just try to think of it, and if you're willing, provide it either in the chat or by speaking up. What would be an example of a situation where you would want to calculate a probability and you would count up some number of ways of an event and divide by the number of ways that anything could happen. Any suggestions?
Maybe a combination lock, like for a locker or something, when you have to guess what the combination could be.
Nice. And so let's not worry about how many different combinations there could be, but you could start with the fact that to get the exact right combination, there's probably only one way to do that. So in that example, there would be one out of however many different possible combinations could be made at all. Then that would be the probability that you would happen to guess the right one, something like that. Does that make sense? That's a good example. I think there's probably homework problems that are sort of similar to that as well. Anybody else want to offer up one? Okay. All right, so try to at least put your mind in this framework as we then look at methods in certain circumstances for how to count up these ways of things occurring so that we can make a fraction which leads to a probability. So the first one is the multiplication counting rule. For a sequence of events in which the first event can occur n ways, and they have a little subscript of a 1 there because there's going to be more than one event. So n sub 1 ways for event number 1. The second event can occur n sub 2 ways, etc. The total number of outcomes is the product of each of those different number of ways that something can occur. So again, let's right out the gate try to imagine an example of this. So an example might be that you are going to the store and you're, so what I'm describing is a procedure that will lead to an outcome, and then we could look at the number of ways of a particular event versus all possible outcomes. That's the idea, but we're going to have something in which we would count up these number of ways as described here. So let's say I'm going to, I'm at a store and I'm going to pick one of 5 sodas and one of 7 types of chips. So I'm going in there, I'm going to get a snack. I'm going to get some chips and I'm going to get a soda. And when I look at the sodas, I have 5 choices for different kinds of sodas, and I have 7 choices for different kinds of chips. So the total number of possible outcomes of which soda and chip did I get? Did I get orange soda and nacho Doritos? Did I get a Coke and some Lay's regular potato chips? The total number of ways of possible outcomes would be the number of ways that I could pick the soda multiplied by the number of ways that I could pick the chips. So this n sub 1 times n sub 2 times n sub 3, those are the multiplication of the successive number of the choices that I had for each of the sequence of events which is going to occur. So I would say something like total possible combos of soda and chips is 5 times 7 or 35. Somehow started erasing there. Questions, comments, discussions about that? All right, so we read this multiplication counting rule, gave a description. I gave a simple example, but we want to turn this description and this show of an example into working knowledge. I did miss a typed in chance to pick a king and a standard deck of cards. Yeah, 4 ways to pick a king, 52 ways to pick anything. So 4 out of 52. Thanks, Hunter. All right, so let's do this. See if you can think of some succession of events, some sequence of events, and the number of ways that each of those events individually could occur, and then you could produce a total possible number of ways that any resulting event or outcome could occur. Just to have this be knowledge that you can apply, that you're beginning to use as applicable knowledge, so that your brain starts to see this as something that you can not just read about, but something that you can apply. So try to think of one. And of course, as always, if you're willing to share one, that's great for purposes of discussion. You don't have to, but even if you don't want to share, see if you can come up with your own example so that your brain starts to see this as knowledge which can be applied instead of just read and understood. All right, I'll give you one more example. Hopefully you're able to think of some, even if you don't want to share. So another possibility is you can imagine that you're going to make and sell some t-shirts, maybe by putting up a stand at DVC. For those of you who've been on campus, or obviously not recently, when they were selling t-shirts, they would often have different types of t-shirt, different sizes. So let's say that you have different designs of shirts, meaning that you have a different thing that you post on the front, maybe some picture of something. And so let's say in your shirt, you have 12 designs of different types that you're going to try to produce and sell. And then for each shirt that you try to sell, you're going to need to have different sizes. And we won't worry about having more of the more popular size, but at least you want to have at least one of each size. And then maybe you'll try to predict which sizes will sell more and have more of those. But let's say your 12 designs need to be available in 4 sizes. So you're going to have small, medium, large, and extra large. And you're going to have 12 different designs. And you want to offer all sizes and all those. So then you can say, how many different possible shirt types will you be offering people? Where you could say you can pick any one of 12 of these designs and you can pick any size that you need. How many different possible shirt results is that? And so you would multiply to get the total possible number of shirts or shirt combos of design and size. You would have 12 designs. Each one has to have 4 sizes for a total of 48 possibilities. Questions, comments, discussion about that? Okay, on we go. So now they give us an example. When making random guesses for an unknown 4-digit passcode, each digit can be anywhere from 0 to 9. There's 10 possibilities there. What is the total different number of different possible passcodes? So there's 4 digits. And so here's a notation that I like to use. When I'm trying to imagine the different ways that the succession of events can occur, not always are each of those different possible successions. Oops, sorry, I didn't expect my phone to be up here. Let's see if I can turn this off for you. Not necessarily each of those succession events will always have the same number of ways that it can occur. And so to have a quick way to illustrate the idea and organize work for the multiplication concept here, you can imagine this as a succession of choices. And each one I write as like a box, assuming I can not erase on top of that. And then I can fill in each of those boxes with the number of ways that that choice could have been made. In this case, they're all the same, but I can say there's 10 ways to pick the first number, 10 ways to pick the second one, and in each case, that'll happen 4 times. And then that leads to a result of 10 to the 4th, or 10 multiplied by itself 4 times, as the total different possible passcodes there could be. So that's a 1 followed by 4 zeros, or 10,000. So I'm illustrating sort of a little annotational trick to help sort of visualize what's going on when you're given a paragraph describing some choices that need to be made, and you're beginning to think about how can I think through this and organize it. Then this is sort of a method. And in a simple example, you might not need to go to this step, but as things get more complicated, this could really help. So questions or comments or discussion about this example of using multiplication counting rule? So I think they're going to come to the same conclusion in slide 2, in this 1 of 2. So then you can follow that up with there's 10 possible ways. Then we could calculate the probability that we were discussing before. And as you can see, they make a fraction in which on the top of the fraction is the number of ways that the event can occur. And the event in this case is that you're guessing the correct passcode on the first attempt. There's only one way that can happen. And then there were 10,000 different passcodes. So that's 1 out of 10,000 is the likelihood that on one try, you could guess the right code. Questions, comments, discussions about that? Okay. So now we extend the rule that we just looked at, the multiplication rule, to a new rule that applies in certain circumstances. This is called the factorial rule. So the number of different arrangements in which order matters of n different items, when all n of them are selected, is written with this n, and it's an exclamation symbol, but that symbol is read as factorial, the word that's above it. So that's n factorial, and I think they'll show you that calculation next. Or not. All right, so before they do that, let me just define it here. I don't know why they wouldn't just do that right there. So what does n factorial mean? So let's give an example. So n is a number like 5, and then you write the factorial symbol after it. So that's read 5 factorial. And so apparently 5 factorial is a calculation that leads to a number, because it says that's the number of different arrangements of n items when all n of them are selected. So this is referring to a number, and this is a formula for how to calculate that number. When you write a number followed by the factorial symbol, then the way you do the calculation that they're referring to here is you start with that number 5, and then you multiply it by each number below it one at a time down to a 1. 5 times 4 times 3 times 2 times 1. So n factorial means start with the n number and start multiplying as you subtract 1 each time until you get down to a 1. And then this, of course, will result in an answer, a number, a value. So in this case, we get 120. So 5 factorial is a calculation that results in the number 120. And that number is then the number of different arrangements for n different items when all n of them are selected. So what does that mean? What do they mean by the number of different arrangements of n items when all n of them are selected. What the heck does that mean? Well, the different ways to arrange things is most simply thought of is how you would list them or how you would line them up. So imagine that I have, we'll say to have 5 things. Let's say I have the letters A, B, C, D, E, the first 5 letters of the alphabet. So how can I arrange these? What does that mean to arrange them? Well, to list them in a particular order. That's why it says order matters. For example, the way I just listed them to you is with a particular arrangement. It's alphabetical. So this would be one example of an arrangement. So there's an example of an arrangement of the first 5 letters of the alphabet. Or I could arrange them a different way just by switching the first 2, B, A, C, D, E. Is also an arrangement. Or maybe I could list them in reverse of alphabetical order, E, D, C, B, A. Anytime I switch the order around a little bit, I get a different arrangement. And so all the number of different arrangements can be totaled when you have 5 items to arrange that are different from each other, and the order in which you arrange them matters. And this calculation tells me there's 120 different ways that I could arrange these 5 letters. So when are the number of arrangements of things something that makes sense in the real world? Well, a very simple example would be just listing them in a particular order in which the order matters for some reason. And one of the ways that that's often done is when you rank things from first to last. So for example, let's say you have 5 horses running in a horse race. Well, then when the horse race finishes, what matters is who was first, second, third, fourth, and fifth. And that is a particular arrangement of the horses. And there's going to be 120 different possible outcomes for the race. Different ways that they could have finished, different ways they could have been ranked by who finished first, second, third, fourth, and fifth. So rankings of things are different ways that things can be arranged. Well, yeah, so there's lots of possibilities. And as we go through examples, you'll see them described. But the structure of what's important here is that you arranged all of them and that the order in which they were arranged matters. And when you do that, that leads to a calculation. Now, you could also think of this based on the multiplication rule that we talked about before. Why does this formula tell you that 120 different possible results could occur? Well, because you can think of it as those succession of events that I was talking about and that the multiplication rule refers to. And the idea is, how many ways could you choose the first letter? Well, there's 5 ways you could choose the first letter because you have A, B, C, D, or E. But then when you're going to list the second letter, if I'm just arranging items and I've already put one of them first, I have the remaining 4 letters to choose from for which one will come in second or be listed second. So there are 5 ways to see who comes in first or gets listed first. Then there are 4 remaining items to choose from to see which one is listed second. Then after I've listed the first 2, there are 3 left to see which is listed third, 2 left to see which is listed fourth. And if you used up 4 of them, there's only 1 left at the end to put in last place. So the multiplication rule that we introduced at the beginning of this discussion gets applied to these circumstances where you are arranging items to lead you to this factorial calculation in that circumstance. So there's two things here. One that they state here, I'm going to begin to focus on. Order matters. So one is that order matters. And two, another thing that had us lead to this is that when I'm arranging objects, I can't use the same object twice. So if you compare this to the passcode example that we were looking at here, why wasn't this 10 times 9 times 8 times 7? Why was it 10 times 10 times 10 times 10? Why don't you have like starting of a factorial or something? Well, the reason is that when you were doing the passcode, when you chose which of your 10 numbers you were going to use, as an example, I might do 5, then I might have the number 5, then 2, then 7, then 7 for my passcode. Well, in each case that I'm choosing a number for my passcode, it doesn't matter which numbers I've picked before. The fact that I chose a 5 for the first number in my passcode, well, when I go to choose the second, I might have another 5, like the 7 repeats here. So that means I still have all 10 numbers to choose from in each case where I made a choice. Whereas if I'm arranging objects, then after I've used one of them up and decided that one's going to come first, I no longer have that one to use anymore. And as I work my way over, the number descends 5, 4, 3, 2, 1, because in each case, the ones that I used before are no longer available to use again. And that leads to this counting down in my succession of events and choices. And that leads to the factorial calculation. So order has to matter. And also, as you go down and you're choosing in your succession of choices, you don't get to pick the ones that were chosen from before. And so the way that you can use a phrase to describe that fact is that you're making these choices without replacement. I'll just write that. Meaning that the choice that I have for the second one, you don't get to replace the number you used in the first one and use it again for the second one. And that as you're making these choices, the things that you're choosing don't get replaced or are not still usable. And therefore, the number of possibilities is going down with each successive choice. So these concepts, when you're looking at a situation, will help you determine what type of formula or calculation you're going to use in order to determine the number of possible ways that something could occur. Questions, comments, discussions about that? So compare the number of possible ways to have a 4-digit passcode with using digits, the 10 single-digit options from 0000 up to 9999. Compare that with the number of ways to arrange 5 letters in this case, and the fact that this is a factorial and that the other one is not. So let's say I describe a situation similar to this one about arranging the 5 letters a little differently to make a comparison. So let's say my second example is that I'm picking letters from a bag, like Scrabble tiles, and I have these 5 letters on tiles. And instead of ordering the 5 things, I'm going to pick one of the letters and look at it. And then I'm going to put the letter back in the bag and write down the letter that I chose. So I'm going to spell a word with 5-letter choices. And I'm going to specify it to use the language above with replacement. Sorry, that's sloppy. So for example, I pick out the letter and I look at it. Oh, I got an A. And I put it back in the bag and I write down A. And I shake the bag up and then I pick out another letter. And then maybe I got a B. So then I write down B and I put that back in the bag and I shake them up and I pull out another letter. Maybe I got A again because I replaced it. I may get an A again. Each time I'm picking my 5 letters from the bag to spell out my 5-letter word, the letter that I've had before will not prevent me from having that same letter again. So in that case, my calculation would be 5 choices. Again, 5 letters are being picked. But in each case, the possibility is the same. I might have 5 to choose from. And so that's 5 to the 5th power instead of 120. And 5 to the 5th power is what? 125 times 5, 625 times 5 is like 3125, something like that. Something like 3,125 possible ways that I could make this 5-letter word spelled out. Compared to 120 is a lot bigger. So here's a perfect example of emphasizing the difference between whether you have replacement or not, with or without replacement. So I could have the arrangement of my 5 letters have occurred by simply pulling them out of the bag and not putting them back. So this first one is without replacement, as I mentioned earlier. And then this second one is with replacement. So I have a bag of 5 letters, and in one example, I pull a letter out and I put the tile down, and then I pull another letter out and I put that tile down next to it until I've pulled all 5 out, and I have a list of my 5 letters in a particular order. Order matters because I spell out a word as I pull them out of the bag, but I'm not replacing the tiles, and I do it until I've arranged all 5 tiles. That's an example of an order arrangement where all 5 are used. That's a 5 factorial, and there's 120 different possibilities. But if instead, if I pull out the letter and then I write it down and put it back, and then shake it up and pull out again and write it down and pull it back until I've written down 5 letters, well, that's 5 items, and order matters, but that's without replacement. I'm sorry, that's with replacement. So that means every time I had all 5 to choose from, so I end up with 5 to the 5th power, or over 3,000 different ways that could occur. Questions, comments, discussions about this example of pulling letters or the factorial rule and when it applies and when it doesn't? So they give this paragraph, which I think was less helpful than looking at examples, but let's write it. Let's take a look. The factorial symbol denotes the product of decreasing positive whole numbers. So they're describing what the formula does. By special definition, 0 factorial equals 1. This factorial expression is going to be used in formulas coming up. And so when you're using a formula that ends up with a factorial, it is sometimes possible that you get a 0 factorial. And so they are defining 0 factorial to be equal to 1 when that happens. And that's how the mathematics makes sense. The factorial rule is based on the principle that the first item may be selected n different ways. The second item, you have 1 less ways to do that, and so on. So that's why it's the multiplication rule being applied. This rule is really the multiplication counting rule modified for the elimination of 1 item for each selection. Now let's see maybe an example that they give. A statistics researcher must personally visit the presidents of the Gallup, Nielsen, Harris, Pew, and Zogby polling companies. How many different travel itineraries are possible? So right away, notice that this is sort of a real world description of something and a goal. And right away, people may lose sight of everything we just discussed. The fact that they're putting in actual places and a goal of visiting people makes it look a lot more complicated for most folks than just picking letters out of a bag or thinking of things like that. And so we have to try to get some comfort with very simple examples that don't have much context, because adding context like this often can make it more confusing than when the context is not there. But at some point, we want to be able to use this in real world circumstances. And so we have to build ourselves up so that we can use the math principles even when the context shows up. So you could imagine this in a simpler form, that you have to list the order in which you're going to visit these companies. And you could even just think of the letters, right? G, N, H, P, and Z. Well, instead of A, B, C, D, E, you could have G, N, H, P, Z. Those are your 5 letters. And you can say, which order do I go and visit these will be the ordering of those letters. You could put them in a bag. You could put these companies' names on pieces of paper and drop them in a hat and then pull them out one at a time until you've pulled out all 5. So it's completely analogous to just pulling letters out of a bag. The structure of the idea of what you're calculating is exactly the same, but there's a little added context. Because what is a travel itinerary? Well, that means just the to-do list for your travels of the day. Where are you going to go first? Where are you going to go second? Where are you going to go third? It's just a list. So the list of letters is exactly the same as the list of the order of these companies that you're going to visit on a particular day. And so in this case, there's 5 of them, and you're going to do all 5, and order matters, and it's without replacement because you're not going to go to the same company twice. And so that leads you immediately to just 5 factorial, which we just saw is 120. Then they follow that up. If the itinerary is randomly selected, like drawing company names out of a hat to determine the order in which you're going to visit them, that would be random. What is the probability that the presidents of the companies are visited in order from youngest to oldest? Well, the youngest to oldest order of the presidents of these companies is a one specific ordering out of those 120 that happens to have the youngest was first, then the next oldest. That's one of those 120 possibilities. And so the probability would be 1 out of 120. Questions, comments, discussions about that? So we are on slide 9. I think I can look at the next 2 slides because they're probably just going to do what I just did for you there. Solution for these 5 different presidents, the number of different travel itineraries is 5 factorial. So look at that. They just jumped to this conclusion. That's the hard part right there. They just do it like it's an observation. The hard part is to recognize that from the description of what they said, that this is an example of what they defined for n factorial. It's an arrangement of n objects where order matters without replacement. You have to recognize that's the structure of that particular problem about how many different itineraries there are. Once you've recognized that, then yeah, you use that formula. But knowing that that's the formula to use in that described situation, that's the hardest part. And they don't do anything other than say, yeah, you just use this formula. Now, I do like the fact that they, in this, follow that up by describing how you would come to that same multiplicative process if you just use the multiplication rule. How many different companies can we visit in our first stop? There's 5. And then after we've gone there, then you look down, all right, there's 4 on the left. Which one will we go to? There's 4 choices, then 3 choices, then 2 choices, then 1. So that's an example of the multiplication rule. And that helps us reiterate why the factorial formula works the way that it does. But nonetheless, recognizing that 5 factorial is the formula that you would use is not trivial, and they kind of make it look trivial here. So there's a big danger. I think this is a hard section for students specifically because of this gap between showing you some formula and helping you understand when to use one formula versus another when random different word problems show up. That's the hard part. And so I've tried to sort of have us think about it. And what makes you choose this is that order matters and it's without replacement. And when order matters without replacement, then you have this factorial situation going on here. So because when you are doing your itinerary, you have to choose these 5 things and the order matters and you're not replacing them because you're not going to visit one more than once, that's what tells you structurally that this would be a 5 factorial calculation. Let's see what their third slide looks like. And so then, of course, the last part, as we said, was to do the probability of picking a particular one of those 120 results would be 1 out of the 120 choices. Questions, comments, discussions about any of that? Can anybody think of an example? Well, I recommend you all try to think of an example of just arranging some objects, what those objects would be, how many there are, and then when you arrange them, whether you would arrange them with or without replacement, and in both cases, how many possible arrangements would there be when there is a replacement of the objects allowed and when there is not. And if you want to share one, that would be great. But either way, try to think of an example so that you can imagine these calculations applied to situations yourself. Anybody want to suggest one? All right, so we have a little less than 10 minutes. So I think what I'm going to do is stop the slides at this point and see if we can just take a look at a problem or two from the homework to see if these concepts in the first 11 slides are things that we could apply to the homework. And then what I will try to do for my second class, which won't feel comfortable for them, is that I'm going to go through these first 11 slides very quickly and then try to do more of the slides later because we need to look at something called permutations and combinations, which build upon what we've just discussed. And I'll see if I can then get to that part and do that with the slides and some more examples and make that a second half of this discussion, which I will also post a video of. So that's my plan. Having said that, let's stop the slideshow share and see if I can instead go find a relevant homework problem. So I'm going to open up homework on, whoops, it's not the right one. I need 4.4. And as I recall, 4 or 5, yeah, 5 looked good. So let's do 5 to get us started. Should be from section 1. Do try again. All right, so here's an example. Notice they just give you a paragraph. This is only problem number 5, and they're not guiding you with formulas or saying use a particular formula. So remember, the slides told us there are going to be 5 methods for counting techniques that they're going to give us in this 4th section. And notice right out the gate, they're not telling us which of the 5 is involved here. So first you have to learn the 5 things, and then you have to learn when to use which of the 5 things. And that's the hard part. You're just going to get a paragraph. And we have to look at the situation described and understand what's going on well enough to then choose the right tool to do the proper calculation. So it says a social security number consists of 9 digits in a particular order. When they say that, that means order matters. And repetition of digits is allowed. That means that it's with replacement. When you can repeat the digit, that means you can use it again. That means it doesn't get used up when you're using it along the way. And that means that you do not have factorials because you're not counting down, because you get the same number of choices each time. So that's all in the first statement. That structure is in the first statement. So this is order matters, and it's with replacement because repetition is allowed. So having said that, it says, after seeing the last 4 digits printed on a receipt, if you randomly selected the other digits, and since there's 9, there would be 5 other digits, what is the probability of getting the correct social security number of the person who was given the receipt? You find somebody's receipt, you see the last 4 digits of their social, what's the chance you could just guess the other 5? Well, again, a correct guess is only 1. And how many ways could the other 5 digits have occurred? Each one has a digit of a number, that's 10 choices. So that means it's 10 times 10 times 10, 5 times, or 10 to the 5th. And the probability of getting it right would be 1. And they want this as a fraction, not as a decimal, divided by 10 to the 5th, which is a 1 with 5 zeros. So that's all you do here. So there was a lot of things going on in the problem that led to this particular result. It wasn't hard to get to, but the pathway to it itself can be hard. The calculation wasn't difficult, but you had to know which calculation to do. That's the difficult part. Questions, comments, discussions about this problem from your homework? All right, let's see if we have time to take a look at the next one. Again, just a simple little description of a situation, and then they're asking for a probability. If you know the names of the remaining 7 students in a spelling bee, so there's a big spelling bee, there's 7 students left, what is the probability of randomly selecting an order and getting the order that is used in the spelling bee? So in the spelling bee, they have the students come up and spell words. You don't need to know those details, but there is an ordering of participation, and that's typically done randomly so that nobody gets a benefit over anybody else. So what is the probability of happening to select the ordering that they end up using when it's chosen randomly? All right, so we have to say, does order matter? Yes, who gets to go in which order matters. And is it with or without replacement? Well, each person only comes up once, so that's without replacement. That means the people in the ordering get used up. That means the number's going to go down, 7 for the first, 6 for the second, 5 for the third, until you run out of people and everyone has been included. So that's a factorial, and that means the number of ways that you could randomly choose an ordering for those 7 people is 7 factorial, pretty much straight off of the definition of factorial. So the probability of happening to guess the right one would be 1 divided by 7 factorial. And that would be in a simplified fraction. So I could do on a calculator 7 times 6 times 5 times 4. So for example, if I pull up this Windows calculator here, well, there's a factorial symbol here, n factorial. That's for doing factorials. And most scientific calculators like $10 Walgreens calculators will have a factorial on them also, because this is a very commonly used calculation. It's not that you can't do it yourself, but if it's 20 factorial, you don't want to have to enter in 20 numbers when you can just do it by a button on a calculator. So this would be 1 divided by, and then I need to find out what 7 factorial is. So I'm going to go to the calculator and go 7 and hit the factorial button, and that gives me 5,040. So that means that the probability of getting the right order is 1 over 5,040. I don't know if it's going to like the comma. Let me take that out just to be safe. It should not mind it, but I'll be safe. So these two back-to-back problems, we needed to notice that in one of them order mattered. They both had order mattering. And then in one of them replacement was allowed and the other one it was not. And that changed whether we used factorial or not. And in both cases, we used the multiplication rule to figure out all the different ways that you could get a particular result, which ended up being the denominator of our fractions. Questions, comments, discussions about that at all?
Yeah, I had a question. How can you identify when we run into those problems that basically use the vocab saying that we don't count a number over again? What is the vocab or words that we're looking for to identify that?
So you just described it by saying we don't count something again. Well, that's the dilemma. There are no set words. There's no words that they're limited to about how they describe that concept, but they do have the requirement of somehow describing a situation to know that that's the situation. And so you can just say it the way you just did, that something doesn't count twice. If you're not able to determine that from the description of the problem, you're not able to come up with the right calculation. So that's part of the vagueness between English and math. Or the real life world is sometimes fuzzy and we need clarity to come up with specific calculations. So for example, in this case, how could we have known that you wouldn't use the same person twice and therefore people there's no replacement with the people when they're being chosen? It says the probability of randomly selecting an order and getting the order that is used in the spelling bee. So we had to know that when people are selected for a spelling bee, one person doesn't get selected twice. That you don't use the same person twice. They don't say that. You have to somehow believe that you could come to that understanding. And more importantly, I think you could do it as long as you're clear that that's required. As long as you know, oh, let me think about this. Is this with or without replacement? If you're focusing on that idea, you can usually figure it out from the problem.
Okay.
But in this case, they didn't say you're not going to have one person, one contestant up twice, right? They didn't say that. We're supposed to somehow know that. Does that make sense?
Yeah, I get it. I understand that.
All right, let me first stop sharing and recording because we are out of time.